Alright, this equation here is called the Legendre equation, and in electromagnetics or in quantum mechanics, when you try to solve a system where it has a spherical symmetry, you end up with this differential equation. Okay, and of course, those equations where this comes from, those are called partial differential equations, which is much harder, so I can't possibly explain how you get this, but we will just try to solve this and see what the solution is like. Alright, as before, we learned that we should multiply this out, so expand this so it's like y double prime minus x squared y double prime minus 2xy prime plus L times L plus 1y. And we're going to assume that L is some kind of a positive integer. Okay? L is like 1, 2, 3, 4, 5, and so on. And also L is 0, but 0 case is a little not so interesting, because in that case you just have y double prime and y prime. If you don't have y, that's almost like a first order differential equation. Alright, so we have this, and then we solve it just like how we solved the other equations by series, which is you set y as the sum of n going from 0 to infinity of an x to the n, that power series. When you differentiate this, n comes down, so you get n an x, and you have to subtract 1 off of n, so it's n minus 1. And then because the very first constant term disappears when you differentiate, n starts from 1. That's y prime. Y double prime, again differentiating will bring down an n minus 1. And you get n minus 2. And another constant term disappears, so now you start from n equals to 2. And these are the things that you plug in to each one of them. And the result is that you have y double prime is this thing, sigma n equals to 2 to infinity n minus 1 an x to the n minus 2, then minus x squared. Again, you have y double prime, so n goes from 2 to infinity n minus 1 an x to the n minus 2. And then this one, this is minus 2x sigma, n goes from 1 through infinity, and you get y prime, which is, y prime is this one, it's n x to the n minus 1, then plus L plus 1 y, and y is sigma n from 0 to infinity of an x to the n. Now we are going to move these inside. We know that for sigmas you're allowed to do that. So negative x can be multiplied inside, so that this thing here can be written as plus negative n minus 1 an. And see, if you multiply x squared with x to the n minus 2, they have the same base, so the exponents add up, so you end up with x to the n power. Same thing here, sigma, n goes from 1 through infinity, negative 2n, an, and then this is x to the first power, 1 plus n minus 1 gives you n. Plus n equals to 0 to infinity of L plus 1, an, x to the n equal to 0. Okay. Now, I didn't do anything on this, but if you look at it, you see that everything else has x to the nth power, but this has x to the n minus 2. So what do we have to do? You have to shift, okay? How do we shift?
N plus
N plus 2. N should be replaced by n plus 2. So you take n, replace all the n's by n plus 2, so that this n will be n plus 2. What's n plus 2 minus 1? N plus 2 minus 1 is? N plus 1. A n plus 2. And then n plus 2 minus 2 will be just x to the n as we want it. And this is the part that you have to think a little bit. If you have n plus 2 equals to 2 and subtract 2 both sides, what's that? N equals to 0, right? So now this sigma starts from n equals to 0 through infinity. So that's the equation after moving all the coefficients inside and doing the shifting. Okay, so we did the shifting. We made everything into x to the nth power. Now we use that factory analogy. You have 4 factories where they don't make toys, they make terms of polynomials. And they're never ending. Once you start working, all the workers will start working and will never finish. They go up to infinity. That kind of sucks. But there's a problem. Not all the factories begin at the same time. The last factory and the first factory, they start at n equal to 0. They're the most diligent workers. But this will be resting at n equal to 0 and only begin working at n equals to 1. And this will only begin working at n equals to 2 and afterwards. Okay? So we're going to track the work for each time n, starting from n equals to 0. Okay? So if we explicitly wrote everything down, this is what we're going to see. So first, at n equals to 0, we're going to see that 0 plus 2 times 0 plus 1, so we're going to put 2 times 1. And because we're looking for some pattern, we're not going to write just 2. We'll write it as 2 times 1, okay? 2 times 1 equals of A2. What do I get from here? Nothing, because they didn't start working yet. It's n equal to 0. Yeah. It's not the time for this one to work. This will produce something. This will be plus L times L plus 1, A0. Alright, so that's what we're going to get at n equals to 0. And n equals to 1, let's see what we get. We get, when n is 1, 1 plus 2 is 3, so I put 3. 1 plus 1 is 2, 3 times 2. 1 plus 2 is 3, A3. Does this produce anything? No. How about this one? Yes, this is minus 2 times 1, A1, plus L plus 1, A1. And notice that I didn't put x to the first power because I'm going to factor the x to the first power outside. So all of these are x to the first power. That's a plus. Okay. So if I reorganize these 4 sums in the order of n, when n is 0, this is what you get. N is 1, you get these. And I factored out the x to the first power outside. Next, when n is 2, well, actually, starting from 2 and afterwards, you have a common pattern, right? So we will not write n equals to 2, but rather just say, well, 2 and afterwards, they follow this pattern. N is 2 or afterwards. I mean, you're consistent, all right? When n is 2 or afterwards, you're going to get terms from every factory. All the factories are working now. And you're going to get n plus 2, n plus 1, an plus 2, minus n minus 1, an, minus 2n an plus l plus 1 an, and all of these will have x to the nth power as its sum. Okay? And then it goes forever. So these will be the ones that are produced that goes forever. Alright, so that's what we get. And then because these sums have to equal to 0 as a function. So this Taylor series has to equal to 0 as a function, which means that all of its coefficient must be 0 in order to equal as functions. Okay? So we're going to have the following result. Let's write down the results. So from the very first line, what do we have? We have 2 times 1 a2 plus l plus 1. a0 has to be 0. Subtract this to the other side, so you have 2 times 1 a2 equals to negative l plus 1 a0, and then divide by 2 times 1. Okay. It's kind of awkward to divide by 2 times 1 when you clearly know that 2 times 1 is 2, but our purpose is to find some pattern, so I'll just write it like this. So that a2 is negative l times l plus 1, a0 over 2 times 1. Okay. And then a3, the next line, that 3 times 2, well, let's mark this so that we know which one to use later. So a3, and then minus 2 times 1 a1, and then plus l times l plus 1 a1 equals to 0. So for this one, I'm going to do a little trick. I'm going to factor this. So the way I'm going to do this is still writing 3 times 2 a3. This is l squared plus l, right? So you get l squared plus l. And then this is 2, so you subtract 2. And this factors as what? L plus 2, L minus 1, A1, right? And I move this to the other side, so that gets minus. And A3 has 3 times 2 in front, so I divide. So I divide by 3 times 2. So that's my result for A3. Okay, this one, I need to put this as 0 too, so n plus 2, n plus 1, an plus 2. And then let's move all these functions to the other side so that it's n times n minus 1 an plus 2n an minus l times l plus 1 an. See, if I need to set this equal to 0, but I moved all these terms to the other side. When you move terms to the other side, sign changes from negative to positive and positive to negative, right? So that's what I did. And then notice that this sign here can be factored by an. And we multiply this, so it's n squared minus n plus 2n minus l squared minus l an.
So factor out an, combine everything else. Right?
Yeah, I factored out an but multiplied out everything. Okay, so we have n squared minus l squared plus n minus L. And if you look at it closely, you'll see that you can even factor more, because how do you factor a difference of two squares?
N minus L. N plus L.
N plus L, n minus L, right? Plus 1 times n minus L, so that n minus L are common, so I can factor it out. Okay, so I'm going to factor that, and that leaves you with n plus L plus 1, n minus L, an. Good? Okay, we're almost done. We still need to divide by this to find an plus 2. So we have an plus 2 equals to n plus L plus 1, n minus L, an over n plus 2, n plus 1. Okay, this holds for n greater or equal to what?
2.
2. That's what we got. So we got the A2. Remember, A0 and A1 are the two free parameters, right? Because this is a second order differential equation. It's natural to have two free parameters, A0 and A1. It also happens that A0 is y of 0, A1 is y prime of 0. So if you provide initial conditions at 0, you immediately have the values for A0 and A1. Okay, so you can almost think of A0 and A1 as something that's given. And then you figured out what A2 is, we figured out what A3 is. And after n equals to 2 or later, you can use this recurrence relation. Remember, we called this the recurrence relation. On the exam, I might put some relatively hard question and then just ask, find the recurrence relation. In that case, you just stop here, okay? All right. But we're not done yet, because we still need to use the recurrence relation to figure out what A4, A5, A6, and so on and so on. Okay. Now, notice that A2 depends on A0. And if you plug in 2 here, then A4 depends on A2, right? And then if you plug in 4 in here, then you're going to get A6 depending on A4. So you have this pattern in the even terms and odd terms separately. So we're going to figure out the even and odd terms separately. They'll kind of make things easier to see. You'll be able to find the pattern easier. Okay, so let's try that. You have, since this holds for n equals 2 or later, we're going to put 2. So n is 2 here. You get A4. 2 plus 1, so that's L plus 3. 2 minus L, so 2 minus L. Over 2 plus 2, which is 4. 2 plus 1, which is 3, of A2. Now, I don't like having 2 minus L. I would like to have L minus 2. Can we do that? Pull a negative out, and then you get L minus 2. So you get negative L plus 3, L minus 2, over 4 times 3. And then we're going to put 8 inside A2. We're going to put that negative L plus 1. So there's a negative L plus 1 over 2 times 1 of A2, A0. That this much is A2, right? We just found it there. So what's that? We have L plus 3 times L plus 1. Let's write it in decreasing order. Negative times negative is positive, right? We have L plus 3, L plus 1, L minus, L minus over, what's the easy way to write down 4 times 3 times 2 times 1? 4 factorial. Now we're going to plug in n equals to 4, which is A6. That gives you 4 plus 1, that's 5. So you have L plus 5. And then 4 minus L over 4 plus 2 is 6. 4 plus 1 is 5. A4. And because we already had this for A4, we can plug that in. But again, I don't like 4 minus L. I'm going to put a minus sign and write down L plus 5, 4 minus L minus 4 over 6 times 5 times L plus 3, L plus 1, L minus 2 over 4 factorial A0. So what's 6 times 5 times 4 factorial? That's just 6 factorial. So it's minus 1, 6 factorial here. And then the top will be L plus 5. So it goes down by 2, right? L plus 5, L plus 3, L plus 1. And then starting from L, you have L minus 2, L minus 4. I'm afraid I don't have any room here. So let me just write right here. Okay, so you have negative 6 factorial on the bottom. You have L plus 5, L plus 3, L plus 1, L minus 2, L minus 4 times A0.
I have a question. Why are we doing like n up to 4, n equals 4?
Because we want to track down the even ones.
So like, where do we go up to?
Until you find some pattern. Okay. And we're going to do that again for the odd ones. All right. So I think we kind of found the pattern here, right? So A6 will be 6 factorial in the bottom, right? And you start from L plus 1 less than 6, and then you go by 2's, right? And then there's the L, and you drop down by even numbers. Okay? So let's write down that result. Actually, let's write it here. I still need this odd value. But let's write down the general solution here. So for A even, so when you have 2n, double of a number is an even number, right? If you take any integer and double it, that's an even number. Okay, so that's how I write even numbers. And then negative 1 alternates. So remember, A2 was a minus, A4 was a plus, and then A6 is again a minus, right? So it alternates between negative 1 and positive 1, so we put negative 1 to the nth power. Now, this is tricky. Sometimes you have to modify this by plus 1 or minus 1 because it's in the wrong place. But if you plug in 2, this is positive, and indeed A4 is positive. So it does agree. So that's the sign that I want. On the top, I have L plus 2n minus 1. L plus 2n minus 3, all the way up till L plus 1. Can't fit in here. Okay. And then L minus 2, all the way up till L minus Well, if it was 4, it goes up till 2. If it was 6, it goes up till 4. So what is it? L minus 2n minus 2. And here you have 2n factorial and a0. Okay. So we worked very hard to figure that out. Alright, now let's erase this part. And we have to work on the odd cases. Let's work on the odd cases. Again, we use this along with this for n equals to odd. So you have n equals to 3 is the first odd number you can plug in. Then A5 is 3 plus 1, that's 4. So L plus 4. And then 3 minus L. Over 3 plus 2, that's 5. 3 plus 1, that's 4. And then A3.
Professor,
yes.
Sorry, where did you get that from? This A and A2 and negative all that? Yeah.
This one?
Yeah, I mean everything, like that whole equation. Where did you like get it from? How did you solve it?
Oh, this one, I tried A2, A4, A6. I figured out A2, okay, when n is 1, what do you get? A2.
A2. Right.
When n is 2, what do you get?
A4.
A4. When n is 3, what do you get? A6. Okay?
I mean,
So-
that's what we did though. We did n equals to 1.
Yeah, we got n equals to 1, 2, 3, right?
Yeah.
And then I looked at it and it looked like it followed a pattern. The bottom was always factorial, with these two numbers being exactly the same. And then the sign always alternated. Negative, positive, so we need this. And on the top, we had something that started from 1 less than this number and was decreasing by 2. So what's 2 less than 2n minus 1? 2n minus 3, right? And if you start doing that, at the end of the day, you're going to end up at 1, right? And there was another part where you start from L, and L minus 2, L minus 4, L minus 6, until you reach 2 less than the 2n. So that's why I wrote down.
Okay, so you just wrote it down like this.
Yeah, so, I mean, if you're not confident, just do one more, A8. Yeah. And at that point, you're going to see that, indeed, it follows this pattern. Okay. So it's just looking at the patterns and trying to see which one makes sense. Okay. All right, and we're going to do the same thing here, so try to follow me here.
Yeah.
So we're going to do A5, A7, and then by A7, hopefully we'll see what the pattern is. Then, yeah. If you, yeah, by A7, hopefully we'll find the pattern. Okay. All right, so again, like how I did before, put a minus so that this is L minus 3. So you have L plus 4, L minus 3, 5 times 4. And then you have A3, which we have here. This is minus L plus 2, L minus 1, over 3 times 2 of A1. Okay. Minus minus is plus. 5, 4, 3, 2. What's that? 5 factorial. So at the bottom you have 5 factorial. The top you see that's L plus 4, L plus 2, and then you have L minus 1, L minus 3 of A1. Good? Alright. Now let's do the same thing for A7. I'll write A7 here. A7. To get A7, you have to plug in 5 both sides, right? So 5 plus 2 is 7. So when you have A7, that's 5. 5 plus 1 is 6. So you get L plus 6 you have n is 5, so you get 5 minus 6, 5 minus L. And then when you plug in 5 here, 5 plus 2 is 7, 5 plus 1 is 6. So you get 7 times 6. And then you have an, but n is 5, so that's what you get. Okay? Good? Now a5 is this, so we're going to plug that in, and also we're going to switch places with the minus. So it's minus L plus 6, L minus 5 over 7 times 6 times L plus 4, L plus 2, L minus 1, L minus 3 over 5 factorial A1. Okay? And what's that? That's negative. You see from L plus 6, all the even numbers are present. And then you get all the odd numbers, L minus 1, L minus 3, L minus 5. Over what? 7 factorial A1. Okay, so we found the odd terms. Now you see that these both follow the same pattern. So we're just going to leave this and try to write down the general pattern for this. Okay. So how do you express an odd number? Even numbers can be expressed by twice of n, right?
Plus 1?
Yeah.
2n plus 1?
2n plus 1. Right? If you have 2n plus 1, it gives you an odd number, right? So we're going to say, let's write here. Okay, so you have a of 2n plus 1. Again, we found that the signs alternate, right?
Yeah.
Signs alternate. So we're going to put negative 1 to the nth power. And make sure when n is 2, you get a5. a5 was positive. And when n is 2, indeed it's positive. So this is indeed correct. So this takes care of this, okay? Now, how should we write down the general form of L plus 6? What's the relationship between 6 and 7? It's 1 less, right? So what's 1 less than 2n plus 1? 2n, right? So what should I write here? L plus 2n. Then what happens afterwards? L plus 2n, then what's the next one? 2n minus 2. You go down by 2, right? Now if you keep going down by 2, eventually what are you going to reach? You have some integer, 2n, you subtract 2 over and over again, eventually what are you going to reach? L plus 2. Yeah. So you're going to reach here. Okay. Even if you start at 100, subtract 2, eventually you're going to get 2. Yeah. So it's you multiply, and then eventually you get L plus 2. Okay, so this much is the general form of this much. Is that good? Alright. Now, what about this? What should I write? In general, it's going to start at L minus 1, and then it'll be L minus 3. And where would it end? L minus?
2n minus 1.
Oh.
5 and 7, what's the relationship?
2n minus 2.
It's 2 less than 7, right? 5 is 2 less than 7. So you put, instead of 2n plus 1, you subtract 2. So that's 2n minus 1. Okay. All over what? Huh?
No.
2n plus 1 factorial. Alright, so you get this calculation, but we're not done yet. We still have to write down the solution. So what is the solution? Remember, y is equal to a sigma of k equals to 0 through infinity of ak x to the k, right? Instead of n, I just wrote k. But that's the solution, right? Yeah. But depending on whether your value is an even number, if your k is an even number, it follows this pattern. If k is an odd number, it follows this pattern. So you have to separate this into even and odd. So you end up with two different sigmas. And that the final answer will be when k is even, you get n from 0 through infinity. When k is 2n, you end up with a 2n x to the 2n, which is this thing. So I have to copy this terrible thing. Negative 1n, L plus 2n minus 1, L plus 2n minus 3, all the way up till L plus 1. Then L minus 2, all the way up till L minus 2n minus 2, all over 2n factorial. That's your an times a0, so this will be times a0 of x to the 2n. So that's one of the summations. Plus, the second, oh, I forgot to put a1, sorry. Everything has a1, right? So the second one has a1. I'm going to factor that out, and it'll be sigma n equals to 0 through infinity of negative 1 to the nth power, and now I'm going to copy this. It's L minus 2n plus L minus 2n minus 2 all the way up till L plus 2. And then L minus 1. Gee, I don't have enough room. Okay, sorry. Let me write it under. So long, I don't have enough room. Okay.
So confused.
Yeah. A1 sigma L plus 2n L plus 2n minus 2 all the way up till L plus 2 L minus 1 L minus 3 all the way up till L minus 2n minus 1 all over 2n plus 1 factorial, and you have x to the 2n plus 1. Okay? Alright, so we have these solutions as the solution of the Legendre equation. Now, I said that L is a positive integer, right? It turns out that depending on whether L is even or odd, these horrible things become 0. Okay, so look, if you want, say, so solution of these equations for, let's say you want L equals to 4. Then if L is 4, then this solution, one of these solutions become really simple. Because some of them suddenly become 0. Which one becomes 0? This one or this? When L is 4. Can you guess? Huh? This one, why? What comes right after L minus 2? L minus 2, what's the next one? L minus 4. What's L minus 4? It's 0, right? So if L is 4, L minus 4 becomes 0. So this solution, which you thought was an infinite series, actually terminates after n equals to, let's see. For this to be 4, what's that? N should be 3. 3 times 2 minus 2 is 0? Okay, so when n is 3, this becomes 0. So only n equals to 0, 1, and 2 give you non-zero solution, and afterwards it's 0. So let's track down what that is. So if L is 4, you're going to get, for n equals to 0, you get negative 1 to the 0th power. L is 4, so 4 minus 1. N is 0, okay? 4 minus 1, that's 3. And then 4 minus 3, that's 1. And when you reach 1, you stop. And then you have 4 plus 1. Oh, no. This is 4. So L plus 1 is... oh, just a minute. Yeah, I just realized that these don't even come true because, see, when n is 0, you don't even get these. The only thing that you get is, yeah, so A2 is an exception. I should have included that. Yeah, so it turns out that A2, well, you have to go back to the solution. What's A2? Do you have your...
Negative L, L plus 1.
Okay, so A2 is... oh, no, A0 is A0. What am I saying? Okay, so A0 is A0. Okay. A2 is... Right. Sorry. A0 is...
It's alright.
A0 is A0, okay? Yeah, because, I mean, what does this say? This is A0, this really means A0 plus A1x plus so and so on, right? So A0 is A0, that's not a problem. So A0 is A0, but then, so it's just 1 plus, and then when n is 1, you end up with just this, and this with a minus with 2. Okay, so it's 4 plus 1, 4, there will be minus with a 2. Okay. And because n is 1, you get x squared. Right? And then n is 2. When n is 2, what do you get? 2 times 2 minus 1, that's 3, right? So that means it's L plus 3, and then you go 2 less than L plus 1, so you only get this much. So you get, since L is 4, you get 4 plus 3, which is 7. 4 plus 1, that's 5. And then we know that's plus. And we know this will be 4 factorial. And then, what about this? It will be 4 and 4 minus 2. X to the 4th.
So the L on the outside is a multiplier?
What?
The L times L minus 2 is a multiplier?
So L is 4. 4 minus 2 is 2.
Oh, yeah.
4 times 2. And it terminates here because if n is 2, 2 times 2 minus 2, that's 2, right? So it only goes, this entire thing only stops here. Right? So you have that, and then this is 4 times 3 times 2 times 1. So 2 and 1 cancels, 4 cancels. So what do you have? You have A0, 1, 2 and 4 cancels. So that's minus 10x squared plus 35 over 3x to the 4th. And then afterwards is 0. So if you're curious, you can put this equation with L equals to 4 and actually plug in this polynomial to see that this is indeed a solution. And this does become a solution to that one. All right, so you can see that when L is even, this is a finite polynomial, and this is an infinite polynomial, an infinite series. Okay. The finite ones are what we called Legendre polynomials because it's a polynomial. It's not an infinite itself. Okay. The other one that becomes infinite, that's called the Legendre function of second kind. So this is, for L even, this will be a polynomial, this will be the Legendre function of second kind. And vice versa. If L is odd, this will actually terminate because this gives you the odd number. So if you have, say, L equals to 7, then at some point when you have L minus 7, it's going to be 0. So this will become a polynomial. This will be an infinite series. So the infinite series one, this term will be the Legendre function of second kind, and this will be a Legendre polynomial. So that's the solution. Well, once again, of course, I don't think there's any textbooks that actually does all the calculations that I did. Mostly they just write down the solution and say this is it, and you can just look up Wikipedia what a Legendre polynomial is. You're going to see a bunch of formulas that describe what it is. And then Legendre function of second kind is actually not used that much. We don't care. It's really the polynomial that becomes useful because when you try to solve Laplace equation over some spherically symmetric domain or quantum mechanics in a spherically symmetric domain, it's the Legendre polynomials that are important.